All right, greetings, scholars. So welcome. This is our last. This is our last week, right? So our last class is going to be this upcoming Wednesday. All right. So today we'll focus on chapter 3, and then on Wednesday we'll focus on chapter 4, and then that'll be it. So this Thursday, which is what, May the 4th, so National Star Wars Day. May the 4th be with you, and this Friday is Cinco de Mayo. Those are the reading periods, so the school should be closed. Final exams are next week. Our final should become available this upcoming Sunday at 11:11 a.m. And it'll be due the following Friday. So the hard deadline is not this Friday, but next Friday for all assignments. It might even be pushed back to that Sunday, right? Instead of the 12th, it might be the 14th. But if you finish by the 12th, you'll be done with everything, right? So I think I may have scheduled everything to be the 14th though, right? But if you finish by the 12th, then you'll be within range, and you might get those 2 additional days. So yeah, what I'd like to do today, again, I'd like to just go ahead. Oh, also I want to encourage you. I think the course evaluations are available, so just be sure to do those. It's you should be able to access it. I think it's available via Blackboard. Yeah, course evaluations and surveys on the left-hand panel at the bottom of the burgundy panel. So that's available. Okay, so what I'd like to do today, we said what, chapter 3. I wanted to kind of go through as many questions from chapter 3 as we can. If you guys have specific questions, we don't have to do chapter 3. If you have questions from like the homework and things of that nature, we can do that as well. Okay. Let's just start with a couple of questions from we'll do like maybe 2 questions from each section. So let's start with like question 8. Checking you guys in Zoom one more time. Go ahead and get this student. Okay. It says, find any relative extreme of the function, list extremum along with the x value at which it occurs, identify the intervals at which the function is increasing over which is decreasing, then sketch the graph. Let's see. Okay. Extrema, right? So the extrema, we're going to be looking at the first derivative. The extrema occur where the first derivative is either 0 or undefined. So we had to do like several tests. I guess I should take some notes. I'm already formulating in my mind how to avoid taking notes. I don't think I charged this pen. Let me go ahead and charge this pen. So. And let me get a screenshot of this. Let's copy and delete. Maybe this will work instead. Okay. All right. So extrema are the intervals over which the function is increasing, decreasing, and constant. Sketch the graph. Okay. Okay. So the original we have is f of x. They have -5 minus 3x minus x squared. I'm going to put it in descending power order. So we have this negative x squared minus 3x minus 5. So then my f prime of x, the first derivative, the power comes down. So negative 2x minus 3. Okay. So if we want to find the extrema, that's where the first derivative is either going to be 0 or undefined. So we're going to set this guy to 0 and solve. I guess we can add 3 to both sides. We'll get negative 2x equals 3. Divide both sides by negative 2. x equals a negative 3 by 2. Okay. So then we need to confirm that this is like a max or a min. Now, just at first glance, we have what? A upside down parabola, so it should be a max. We just need to confirm it. We can confirm by doing test values using the first derivative test on either side of this critical value, right? So, like for instance, if we consider the x-axis and our critical value of negative 3/2, we want to look at the sign of f prime, all right? So this is 0 in the first derivative. A number to the right is like 0. So if we plug in x equal to 0, we get a negative result, right? So that means the original function is decreasing on the right of this guy. And then on the left of negative 3/2 is what? Something like negative 2. So if we plug negative 2 into the first derivative, this is going to be 4 minus 3 is a positive 1. So we get a positive result on the left. So that means the original function increases, which is what we anticipated. So left of our critical, we're increasing. Right of our critical, we're decreasing. That implies that this is a max value. So it occurs when x is a negative 3/2. To find the corresponding y, we plug that back into our original. So to do that, I'm going to use my trusty, dusty, rusty, this guy. Come on. And I hope everyone had a good weekend, got rest, a nice balance of what you have to do with what you want to do. Right? I feel like life is not supposed to be all fun and I mean all work and no play. Right? You got to have a decent balance, right? So the original, we have this what? Negative x squared minus 3x minus 5. And then I'm going to call on that function and plug in when x is a negative 3 by 2. I'm also going to go ahead and hit math as a fraction. So we get negative 11 by 4, right? So we have a max value, max of negative 11 by 4 at x equals negative 3 by 2. Okay. So if we have a U-shaped curve, right, we can just choose like a few. It should have a symmetry about x equals negative 3/2. So whenever we get a point on the right, we should automatically get a point on the left. For instance, like when x is -1, like we plug -1, you can just basically choose a few additional points. So to make that -1, I'm gonna just change this to a negative 2 by 2. So half a unit to the right, we get -3. So if we go half a unit to the left, we should also get -3. So basically when we plug in -2, we should also get -3, right? You can use the axis of symmetry to generate a bunch of points, right? Okay, I feel like it's not too terribly bad. Okay. So I think we're ready to answer the question. While we're typing, charge my pen. Okay. All right. Describe the relative min. So we had a relative max. Type in ordered pair. So we got a relative. Oh, let's get rid of this. Oh, we got you now. That's right. Yeah, we didn't have any men. No, right here. Yeah. Order pair, so we got a negative 3 by 2, comma, what do we say? Okay, I'll be right back because I realize that you can't see. I'm just gonna submit this part. negative 11 by 4. Negative 11 by 4. Check that answer. Okay, let me bring the image back. That right here. The student. Okay. All right, and let's do, I think we are still streaming, so let's go share my screen. Let's suppress this and start the broadcast. Okay. So the only other thing is I need to get my confirmation that the image is being pushed. Let me see. I should see the question right now. Oh, it's looking good. Okay. All right, I'm gonna go with it. I can see it. Okay. All right. So the information that we have for the first part was correct. Oh. Come on. Okay, we'll go like this.
Yeah, Professor.
Yes.
What was the answer to the first question?
Yeah, I'm trying to. Devices. Okay. So the first part says describe any relative extrema. So we had a relative max value of negative 11 over 4 when x was a negative 3/2. So we put in an ordered pair, right? We had a maximum at the ordered pair negative 3/2, comma negative 11/4. That was the only thing I submitted, right? That's what we, did by hand or whatever. And then, so the next part, identify any intervals over which the function is increasing, decreasing, or constant. So we saw here, right, when we did the first negative 3/2, the function was increasing. To the right of it, it was decreasing, because remember, we also have an upside down parabola. So it was increasing from negative infinity to negative 3/2. Let's submit that one. Was there a second one of those? I'll get it later. They said it's increasing right here. Parentheses, negative infinity up to a negative 3/2. No, that's not a negative. Negative 3/2. Okay. And then it was decreasing, parentheses, from a negative 3/2 up to infinity. Okay. Let's check this. Okay. So upside down parabola, we said what? Negative 3/2 and then a negative 11 over 4. So this, it's almost a negative 3, and it's upside down. I think it's what, C. C is the only one in the right orientation, in the right position. Okay. Okay, let's go into the next section. That was 3-1. We're going to choose, anybody got a favorite number, like 1 through 20 or 1 through 30? So that was 3-1. Let's use 3. Let's go to 3-2. That's you. And we'll just kind of hop around. Maybe a faster way is if I go here, if we go to manage. I'm going to create an assignment, create homework, and I'll just do it from here. I should be able to just do it from here. I'm just going blah 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 because I don't intend to save this. I think we're focused on chapter 3. So we did 3-1. Let's just choose a question at random from 3-2. If it's 617, so the closest number to 17 I can find. Let's do 3 to 19. I'm not liking this view though. Copy, show, insert. I don't like how this looks. Okay, I'm not feeling this, so I'm gonna get rid of this. Is there a way I can just? No, I'm not liking it. Let's get rid of all of this. Yeah, get rid of this too. Oh, that's what I wanted. That's okay though. I'll just do it from here. It's not a big deal. So 3, 2, second derivative to find max and min. I'm just going to choose question 7. Okay. Determine which graph is the derivative of the other and explain why. Okay. So let me see. We have what? 1, 2, 3. So if I look at P, I have 1, 2, 3 turning points. So more than likely that's a degree 4 polynomial. And then if I look at R, it looks like I have like 1, 2, 3, 4. So it looks like that might be a degree 5. So it looks like P might be a derivative of R. And I'm basing it on the number of turning points, all right? Because if you think about squared, a quadratic function, that has at most 1 turning point, and that's a degree 2. P, I can see 1, 2, 3 turning points. So it could potentially be a degree 4. The other for R, I see 1, 2, 3, 4 turning points. So that means it could be a degree 5. So it looks like P more than likely is a derivative of R. Let me see, the function P is a derivative of R because the function R is not C, is not D. Now let's see, the function P is a derivative of R because P equals 0 at all the values where there has a relative max or min. Okay. Okay. Maybe. Let me see. The function P is a derivative of R because R has because P equals 0, because where R has an inflection point. Okay, so if we have a degree 5 polynomial, we take the derivative and set it equal to 0. If we take the derivative and set it equal to 0, what does that tell us? That's telling us max and mins. This has 1, 2, 3 zeros. And they are, but we had 1, 2, that's a candidate. I mean, it could be. So it's either A or B. I just got to find the difference between the two. At all values of X where R has a relative maximum, where R has an inflection point. That's going to be the second derivative, right? So the points of inflection is where the second derivative would be 0. And so I don't think it's B because that's about the second derivative. So I'm just going to go with A and submit that one. Okay, let's do another one. That was interesting. Assume the function is differentiable over all reals. Classify the following statement as either true or false. If the statement is false, explain why. If F has exactly 2 critical values at A and B, where A is less than B, then there must exist exactly 1 point of inflection at C such that it's between A and B. In other words, exactly 1 point of inflection must exist between any 2 critical values. Okay, let's think about this. 2 critical values, A and B. So that's where the derivative is either 0 or undefined. And then there has to be an inflection point. 1 point of inflection must exist between 2 critical values. I feel like that's false. Inflection points always exist in pairs. So 2 inflection, you see the statement is false. There can be multiple inflection points between 2 critical values. I don't know. The statement is false. No inflection points can, no, it's not that one. There can be multiple inflection points between two critical values. I'm trying to think if I can, because I'm thinking of something where, you know, because like I'm thinking like the reciprocal function, right? You have critical values where it's undefined, but there are no points of inflection, right? If f has exactly two critical values, there must exist exactly one inflection point. I don't think that's true. The statement is false. Inflection points always exist in pairs. So two inflection points, no. The statement is false. There can be multiple inflection points between two critical values. No inflection points can exist between two critical. Any potential. What is this one? There can be multiple. No inflection points can exist between two critical values. Yes, that is possible. Any potential inflection points will either be less than the smallest critical value or greater than the largest. I'm leaning towards D. Let's just go with D. Inflection points always exist in pairs. No. Can there be multiple inflection points between critical values? No, I'm not seeing that one either. I'm gonna go with D. I'm not sure. If it has exactly two critical values, then there must exactly be A. Let me see. Consider the graph. Okay. It could be inflection points. There can be multiple inflection points between two critical values. That's the one I wasn't seeing. So a critical value. Oh, there's one point of inflection, a second, a third. Oh, okay, I get it. So in the middle, right? The critical value is like when x is -2 and x is 2. So we have a max and a min, but we have inflection points without having a critical value, right? That's the image I wasn't considering. Yeah. Okay, that's fine. Can't win them all. Okay, let's try that one again. Is it going to change? So it can't be multiple. That's the one I wasn't seeing. I didn't even think about it. Okay, that's fine. On to the next one. Let's try another one. Assume the function is differentiable over this. Classify the following statement as either true or false. The function can have a point of inflection at a critical value. Let me see. The function f can have a point of inflection at a critical value. Let's see. I'm trying to think if I can. So where it goes from concave up to concave down, I've never seen that. A function can have a point of inflection at a critical value. I wouldn't say that's false. So point of inflection can only exist between two critical values. A function has a critical value. It will not. No. The function can only have a point of inflection at an extreme. Okay, I'm going to go with B. Let's see what happens there. Man, I'm just getting these all wrong. Let me see. Have a point of inflection at a critical value. Concave up to concave down. Oh, I guess it's like what we just saw. Man, I don't know why I'm ignoring that image. Yeah, see, that's like what we just saw, right? It's a critical value. Like, okay, this is the case where, you know, if it does flatten out, but it's not necessarily a max or a min. Just because it's a critical value doesn't mean that it's a max or a min, right? So that's the image. Yeah. All right. So it is a critical value, and it does go from concave down to concave up, but it's not an extreme. Man, these are good questions. So I like these. Let's do another one. Graph the following function, then estimate any relative extrema. Let me see. So it's a degree 5. If we were to expand this, it looks like the leading coefficient would be negative. So it should go down to the right. Is there only one going down to the right? Okay, so I think it's A. Okay. What are the coordinates of the extremum? So we would have to look at the first derivative. Select the correct choice. Let me see. There are 3 relative extrema in order of increasing. Let me see. We might need to expand this guy. Estimate. What are the coordinates of the root? Select if necessary, fill in the answer by your choice. Okay. I'm trying to think if we need to do this without expanding. Because we need to look at the first derivative. Now we could use the product rule. I was gonna expand out that cube function, but let's take some notes here and let's try to find this first derivative. Let's see what happens. Let's copy and delete. Space. Okay. It says, the only thing that's throwing me off, it says estimate the relative extrema. Now, I mean, we could expand this out, like just FOIL. I'm going to try the product rule, right? So let's look at f prime. So the first times the derivative of the second, so then the 3 is going to come down. We're going to have this 2 minus 3x. That's going to be squared times the derivative of the inside function is going to be what? A negative 3. So the first times the derivative of the second plus the second times the derivative of the first is 2x. We want to set this to 0 and solve. Can we factor anything? They both have the 2 minus 3x, okay? Is there a 2x on both of them? No. But we can factor out 2 minus 3x. They both have at least 2 of those, okay? So then it looks like we're going to be left with, what is that, a negative 9x squared? And then we're going to say plus, we still have a 2 minus 3x here, and we also have a 2x here, okay? And we want to set this to 0 and solve. Let me simplify it down just a little bit more. 2 minus 3x squared. We're going to have this negative 9x squared plus 4x. 3 times 2 is negative 6x squared. Okay, let's go a little bit further. 2 minus 3x squared. What is that? Negative 15x squared. So it's like 4 squared equals 0. Okay. So then from here, zero factor property set each thing to 0 and solve. So then we get, long story short, we're going to get 2 minus 3x equals 0. Add and divide. X equals 2 by 3. Okay. And then the other one, if we set this 0 and solve, we're going to have this 4x minus 15x squared equal to 0. We could factor out an x from both of those guys. Yeah, that wasn't completely factored, but that's okay. If we factor out x, we're going to have 4 minus 15x equals 0. So we can do zero factor property again. Long story short, we get x equals 0 as a result. Add and divide. X equals 4 by 15 as a result. Okay. Okay, we have a multiplicity of 2 there. Is it 4? I feel like there's a 3 missing. We had 2 there. I feel like it should be a total of 5. Oh, prime, right? So it should be 4 total. Since that's a multiplicity 2. Okay, so we're good to go. Okay. So now let's see if we can answer the question with these results. Okay, so it says, what are the coordinates of the extrema? We need to verify if these are extrema or not. Okay. So these are critical values. Like these are candidate to do. We can use the first derivative test. 5. So that's like 10. Okay. So then we have our 0 here. We have our 4 by 15 here. and we have our 2x3 here. I put these in order. Okay. Let's look. If we were to look at f prime, we got it down to this line. Let me copy this. Copy. So f prime is this. Okay. So when we plug in, like these should be zeros. These are all our zeros. Okay. So something to the, and actually what I'm going to do, I think I'm going to use my calculator. Come on. I forgot how. Let me see if I go. Come on, go away. I forgot how I used to get rid of this. There we go. Okay, man, that was a pain. All right, let's try this again. There we go. I want this one. Okay. My device is not come done. Reload and refresh. Okay. I'm just going to type this derivative in because I just want to call on it as a function. 2 minus 3x quantity minus 15x squared. Okay. So then we can verify our results, right? So when we call on that function, when we plug in 0, we should get 0. When we plug in 4/15, we should get 0. And when we plug in 2/3, we should get 0. Okay, so we verified that those were indeed 0. So then if we choose something to the left of 0, namely, I'm going to plug in -1. Okay. We get a negative result. All right. When we plug in -1, we got, let's do this in this color. We got a negative result over here. That implies the original function is decreasing. Okay. I'm going to do 3/15, right? Just something to the left between 0 and 4/15. So I'm going to plug in 3/15 because I know that's going to be between the two. We get a positive result, right? So that means the original function is increasing between these two. And then to the right, I think 5/15 should work. We get a negative result. So the original function is decreasing. Let me see. That's 10. So I'm going to do 11/15 for the final one. And we get a negative, right? Oh man, wait a minute. Okay, so we didn't get an extrema there. Yeah. Okay, so we only got 2 extrema, right? I kind of wanted that final one to be an extrema, but it looks like it's not, right? So if we're going from decreasing to increasing, this is a local min. Thank you. Stop. So this is a relative min, and this is a relative max. And then the last one is neither. Okay. So let's hop back here and do it. Come on. There you go. Okay, so what are the coordinates of the extrema? We got 2. Yeah, so we're gonna go with B. In order of increasing X values. Let me see, it says type an order pair. So we need to find the corresponding Y's with those X values, okay? So what I'm gonna do, I'm gonna type the original into slot 2. I wanna keep that first function I have in there, that derivative. I just wanna keep that for now. And so I'm gonna put the original into slot 2. We have X squared, parentheses 2 minus 3X to the power of 3, okay? So then I'm gonna call on that second function. And we wanna evaluate it so the X values that we got when X is 0 and X is 4/15. So when X is 0, we get 0. And then when X is, what do we say, 4/15? I'm going to hit math as a fraction. We get that result. In order of increasing X value? Okay, so here goes nothing. It's making me a little nervous. I was like, I feel like we missed something somewhere, but let me see. It says separate, type an order, type an integer or a decimal, round it to 3 decimal places as needed. Okay, that's fine. We'll fix that. So when X was 0, we got the origin. So 0, 0. No, not 3. It's B. We got the origin. And then this other one, I'm just gonna recall that, but remove the fraction thing. It said 3 decimal places. So 0.123. Okay. Let's do 4/15. 3 decimal places, so 0.267. I'm not confident in this. 0.267. We got 0.123. Okay, well, that's okay. All right. So again, this, that's what we got. Okay, was that it for that one? That was a good question. Those were interesting. What's the time? Okay, let's go to the next section. So that was 3-2. Let's just go into 3-3. View. Allow. Okay. Okay, let's do like 1 or 2 from here. Just do 8 again, I guess. Okay. Determine the horizontal asymptote of the function. If none exists, state that fact. Okay, so I tend to do these the way we did them in college algebra by doing a test. I think the way the text does it, like we could factor out an x from every term on top and bottom. That's going to leave us with 4/12 minus 5/x. As x goes to infinity, we're going to be left with 4/12. And I think it's something similar for negative infinity. All right, 4/12 reduces down to what, a third. One horizontal asymptote, y equals 1/3. Y equals 1/3. If I need to write out those details, just let me know. See, determine the horizontal asymptote of the function, right? So for this one, it looks like if we factor, like the highest power is x to the power of 6, right? So if we factor out x to the 6 from every term, right? Notice that so like all the terms are essentially going to go to 0. We're going to be left with a 4 on the bottom. and that numerator is going to go to 0. So then if the numerator goes to 0 and the 4 is on bottom, 0 over 4 is 0. So it has one horizontal asymptote. It's going to be y equals 0. Y equals 0. Okay. Again, if I need to go through those details or write something out. Now, I could explain how we do this in college algebra as well, because it's done a little bit different. It's the same concept. It's just done a little bit different way. Sketch the graph for the following function. Indicate what the function is: increase or decrease. Asymptotes. Sure. I guess we could do this one. This one will be kind of fun. So I'll do this one by hand. Hopefully, it doesn't eat up too much time. This can be can kind of go a little while. Let me see. Yeah. Let's do this one by hand. So I know we don't have a lot of time, but I think it'll pull on a lot of relative concepts that we talked about. So let's copy and delete.
Professor,
Yes.
I actually have some homework problems that I kind of want to.
Yeah, we can do that. That's fine. Just go ahead and do the Ask My Instructor, because this one will eat up a lot of time, and I don't want to. I'd rather just go through the ones you have questions you had specifically.
Oh, okay.
We got at least 30 minutes, in class right now. Hopefully you guys were able to get outside and take a breath. I know we're entering finals. I try to make it as light as possible. I know that some of these questions are bizarre. But I feel like with us not doing testing in a testing environment, and you get unlimited attempts, I feel like that's enough of a cushion, to try to, anybody that wants to get through can get through, you know what I mean? Since because of the structure, because of the way we have everything kind of set up. Let me check on you guys in Zoom. Yeah, he must have got knocked off. Okay, let me see. Oh, wow. Okay. Okay, so I see 3 of them. Okay. Let's pull up the first one. Let's kind of hang out over here. Like this. Okay, that's fine. Evaluate. Yeah, I can share it right here. Okay. Let's start by getting a copy. Okay, let's copy and delete. I'll drop it right here. Boom. All right. Okay. Ask my instructor, evaluate. Let's see. So we're doing integration by parts, right? Okay. So UDV. So we need to find our U and we need to find our DV. That's our u. Okay. So what if we, let's try this. Let's see, let's let our u, I'm thinking let u be, yeah. Let u be 3x plus 5, okay? And we're gonna let our dv be x dx, okay? So then the integral of x dx, I chose that because it's easy to integrate. So then that means our v will be what? X squared over 2, and our du will be 3. Okay. Let me think about it for a moment. We might need to change, let me see. Because if that's our u, but then we would have what? We have that fourth root in there. If we let our u be what, the fourth root? What if that was our dv? Can we integrate that? We add 1. That doesn't seem like it's helping. If we let our u be fourth root, the 104 comes down. That doesn't seem like that works either. Let me think about it. Oh, ow, ow, ow. Ho, ho, ho. So it's a matter of finding the proper u and dv. Now, I don't think that applies here though. Let's see. I'm gonna have to use this. Because I know sometimes it's like, let's just look, let me see, let's do an example. Given, no, so again, a challenge. So we're good there, right? And then, so our du, yeah, we got that. So then for x, oh, a substitution. Okay. It looks like they were using substitution instead of integration by parts. Let me just check one more time. Because if we do substitution, I think we can get it. Let's see what they do. Yeah, they're doing substitution. Okay, so let's try that with substitution. So maybe we were just trying the wrong technique. Where'd it go? Okay. So let's try this one by substitution instead of integration by parts. Let's try that. I didn't even think about it. I automatically went to integration by parts because of the section. So let's try by substitution. All right. So this looks similar to like what we were doing last time. So let's try substitution instead of integration by parts. That's kind of how it goes. Sometimes you try one technique. If it doesn't work, you try something else. So let's try, let's see, let's let u, we got the 3x plus 5, right? So then that means our du was just 3 dx, okay? And then they expressed, we wanted to solve for x, right? So then if we subtract 5, we get u minus 5 over 3 equals x, right? So then if we make those substitutions, x is going to be what? U minus 5 over 3. You still have this fourth root of u. So dx, so we need to say 1/3 du equals dx. All right, so now it can match. So then that means we have a third out here, and then there's a dx here. Okay. Sorry, du. Okay. Now, are we doing integration by parts? So are U and a dv? Let me see. Because we got a U by 3, we got a 5 by 3. That's not helping us. We're not getting rid of that. We can integrate that. Can we let that be our U? I'm going to see what they did next. So we did the substitution because it looks like they went from substitution to integration by parts, right? We got all of that. That's fine. U right here. U minus 6. Okay, so it looks like they expanded, right? Oh, okay. Okay, so they expanded it. Okay. So we're there. We're just gonna expand it. And then once we expand it, then I think if we rewrite this guy, right? If we expand it, that 3 can go in front, so it's gonna become 1 by 9. Okay. Now we're gonna have U to the 1 times U to the 1/4 becomes U to the 5/4, U to the 5 by 4. And then it's gonna be minus 5 U to the 1 by 4. And all of this is du, okay? All right, so I think now we're ready to integrate. That was interesting. So now it's like normal. We add 1 to the power. So that becomes what? U to the 9 by 4 over 9 by 4. And then add 1, that becomes minus 5, and we need to distribute that 1 by 9. U to the 5 by 4 over 5 by 4. Okay. And then we still have plus some constant. Okay. If we flip and multiply, it becomes 4 by 9. Okay. So we're going to have a 4 by 9 times a 1 by 9. And okay. And we still have this U to the 9 by 4. If we flip and multiply, 4 by 5. So the 5s cancel. Okay. So we're going to have 1 by 9 times what? 4 times U to the 5 by 4. Okay. Plus some constant. Okay. Okay. So then we need to put U back. 3x plus 5. Okay. So then it looks like it's going to be 9 times 9 is 81. 4, what was it again? 3x plus 5 to the power of 9 by 4. 4 by 9. 3x plus 5 to the power of 5 by 4 plus some constant. Man, that was an adventure. So, you know, with this one, it ended up being substitution, right? Let's make sure we got this correct, and then we can go back and like walk through this one again. That was interesting. Okay, so this is the result that we got. Let's make sure it's correct, and then we'll go through it one more time. Let's see. Maybe I can just pause this. No, go back. Okay, it'll pop back up in just a moment. Go here. Here. Come on. Okay, that's what I want. Okay, let's give it a go. Let's see. Cross our fingers. Hopefully we kept our mistakes to a minimum. We got 4 over 81. Let's try that again. 4 over 81 Now parentheses, let's just do a double parentheses. We got to the power of 9 by 4. Inside the parentheses, 3x plus 5. Okay. Minus what? 4 by 9. 3x plus 5. The power of 5 by 4. Some constant. Cross our fingers. All right, that was an adventure. All right, let's recap that one more time. Right, that was fun. So the first thing was, I was trying to do integration of parts. I couldn't get it to work. Turns out the suggestion here was that's fine. The suggestion was substitution, right? So let's hop back here. Back and let's go like this. Right. So it ended up being substitution. So we let our u be 3x plus 5, and that our du was what? Just 3 dx. But then we had an extra term on the outside, so that came from over here. We manipulated our u, so subtracted 5 and divided by 3. So then this is an expression for x. So we replaced x with this u minus 5 by 3. You see it here. And we substituted our u here. Okay. So then from there, we expanded, right? So we have this times this. So I factored out that 1/3. That's how this became 1 by 9. And I also distributed this u to the 1/4 into this guy. So that's where this 5 by 4 came from and this 1 by 4. Okay. So then from there, we were able to integrate. So we added 1 to the powers and divided by the new power. That's where the 9 by 4 came from and the 5 by 4. Then we put the substitution back and distributed the 1 by 9. All right. You just had to kind of keep it neat and organized. That was actually a really good question. Like, I really like these questions that Mr. Lowe brings to me, because then it's like, it makes me think, right? I had to think and figure out. And I've actually come across some techniques I personally have never done. I think I've seen them, but I didn't get it until this time. Some of those concepts, right? As far as how to do it. But yeah, so it kind of pushes me, and I'm like, okay, cool. And it's like certain things I may have seen them in the past, and it wasn't sinking in, but it definitely sunk in this time. I was like, oh, I get it now. I see the technique. Just sometimes I do forget to use the technique, but I know it's there, and we can kind of walk our way through it. Okay, let me pull up the next one right here. Oh, he sent another one. Cool. He's coming through with the. Let's pull up another one. And I still feel like this is a useful interaction, even though you guys have access to the Axiomer instructor. I feel like I can see the nuances a little bit better than you guys can. So it's like, between the two of us, between using all our resources, we can get to the bottom of what's going on. Check the differentiation, evaluate. Okay, let me just share. Right? Because I feel like, seeing that was substitution and not integration by parts might not be that obvious. And then again, some of the other nuances. And so, we were able to get to the bottom of it. We just want to evaluate this guy. So now I'm like, well, dog, are we going to use substitution or are we going to use integration by parts? But, let's just try. What was like this? I'm trying to think which one am I feeling? Let's copy and delete. U and then DV. So we want to integrate. If that's our U, and we want something to cancel our DV. Okay, I'm going to try integration by parts. Again, you saw what happened in the last one and see what happens. If we can't get it to work, we can try substitution. If we can't get that to work, then we'll look at the view and example. Hopefully it has a view and example. They don't always have it. But I'm feeling my intuition is saying try integration by parts, okay? So we're going to try integration by parts to start with. So I'm thinking usually when you do the integration by parts, you're able to get one of the powers to decrease. So I'm feeling like maybe let our u be 3x and our dv. When you choose your dv, you want something that you can integrate, right? Let our dv be e to the 8x dx. Okay. Okay. So then with this, our du will be what? 3dx. And our v, if we integrate, now the integral, let me see, of e should be itself e to the 8x, I think, divided by 8. Let me see. The derivative of e is itself times the derivative of the power, right? They should cancel. We should be good to go. Okay, that's our v. So now, if we apply integration by parts, the original is going to become, so the integral of u dv is going to be u times v. So it's going to be,
Professor,
yes.
why is v e to the 8x over 8?
Take the derivative of this guy. When you take the derivative of this, do you get this? All right. If you take the derivative of this, remember the derivative of e is itself times the derivative of the power. So when you say times 8, it's going to cancel, and you should finish with this guy. You should finish with this.
Morehouse?
Right? Unless I made a mistake, but that should be what it is, right? Okay. So now if we say u times v, let me see. Is that okay?
Yes.
Okay. So let's do 3 over 8 x e to the 8x, right? That's uv minus the integral of v du. So the integral of v du. So we're going to have 3 over 8 e to the 8x dx. All right, that does look, the power did come down. I think we can actually integrate that guy. All right, okay. So then we get 3 over 8 x e to the 8x. Okay, that 3 over 8, we can just bring it in front. Okay. The integral of e, we just did it. E to the 8x is going to be itself. So it's going to be e to the 8x over 8 plus some constant. Okay. And then just to kind of bring it all home, 3 over 8x e to the 8x minus 3 over 64 e to the 8x plus some constant. That's what we get. That one wasn't as bad. Yeah, man, like that's how these questions go. You never really know what's going to happen. I mean, hopefully, I know you guys are stressed out. Like I could feel it. You could just feel the energy, right? I just hope you can like just push, right? And like get through this and get your stuff submitted. Hopefully you guys have gotten your exams where you want them to be, you know. You can take the past material, sit down with the tutors and work together. Like it's totally okay. Just all I'm gonna do is pull whatever's on Pearson. You can ask me questions. We can work on it together with the tutors, because all I'm going to do at the end is whoever's still in the class, I'm going to pull the averages from Pearson and use it to calculate final grades, right? Because again, the intent of this is not to be super rigorous, even though I know the questions can be kind of super curveball-y. So because of that, again, that's why I do unlimited attempts with a minimal late penalty, right? So, as long as you can get it in there. I want to get a screenshot. Not a screenshot. I just want to. How do we catch up? Can you just catch up to the live? Let me see if I go like this. I click on live. There we go. That's exactly what I want. Okay. Okay. I'm gonna hop right here. Let's submit this result. Oh, okay. So which of the following shows the correct u minus the integral of v to u formation? Okay, so we got 3 by 8x e to the 8x. Let me see. Let's zoom out some. Let's see. So I think the only one that has the right form is B. We got 3/8 x e to the 8x minus the integral of 3/8 e to the 8x dx. Yes, let's go with B. That was already chosen. I don't know how, but it was there. Okay. So then the result that we get is right here. Come on. All right. This one. All right. You see, we get 3/8 x e to the power of 8x. Okay. Minus, we got 3/64. Okay. E to the power of 8x plus some constant. All right. Awesome sauce. Okay. Let's catch up to the live. Let's hop back right here. Okay. And let's go ahead and do the next one. Okay. Right here. And I want to share with right here. Okay. So the next one, evaluate, check by differentiating. Let me see. And I think we just did one like this, and we use substitution. Are they doing? It looks like they're doing integration by parts. Okay, so similar, right? Let's get a screenshot. We're going to copy and delete. Here, let's get some fresh space. That's enough right there. Let's paste. All right, let's try integration by parts, right? So the little prompt that we got looked like they were doing integration by parts. So we're going to try something similar. Let's see. Let's let our U. Let me see. Oh, okay. So we're essentially at the end of class. I don't want to keep anybody that needs to go or wants to leave. So our last class is going to be Wednesday, just kind of more of the same kind of thing. You know, again, the final exam should become available this upcoming Sunday at 11 a.m. I would encourage you, you could take this content and you can sit down with the tutors or work together and you can submit the stuff. Just work on it. My real intent or goal with this was just expose you to these concepts and encourage you to try, right? So it's not like super rigorous. It's in an environment of your design. I just want you guys to kind of submit it for right now. If you can ask me, we can work together. Just anybody that you're comfortable working with, just however you can get it submitted, we got about 3 or 4 other questions, so we're gonna kind of power through and try to answer a few more. But if you need to go, I'll release you. And from one beautiful mind to another, take care, and I'll see you guys again on Wednesday. Again, we're going to kind of keep going at this point. Okay, so with our DV, we want something that we can integrate. Let me think. I totally want to use substitution like we did before, but it looked like they were doing integration by parts. If our U were X, right? And we can integrate that. I think so. Okay. So if our U is X and our DV, I think we can integrate this. We got this 4th root of X plus 6 dx. We're going to try in just a moment. That means our du is going to be dx. Okay. And our v, let me see. So that's to the power of 1/4. Okay, so if we add 1, I think we're going to have this x plus 6 to the power of 5/4 over 5/4. Let's see if we take that derivative, right? Does that work? So the derivatives guy, the 5/4 comes down, they cancel. You subtract 1, you're going to get your 1/4 times the derivative of the inside function, which is just 1. So I think it's okay. It looks good. Okay. Okay. So we were able to successfully get all the parts. So then the original now is going to become, so the integral of u dv equals u times v. So if you flip and multiply, that becomes a 4/5. We got this 4/5x times this x plus 6 to the power of 5/4. So that's uv minus the integral of v du. Okay, so that's also the 4/5 persists there. We got this x plus 6 to the power of 5/4 dx, right? And I think we can integrate that similar to what we just did a moment ago. So 4/5x, x plus 6 to the power of 5/4. Now when we integrate that, that's going to become what? 9/4 over 9/4. So 4/9. So that's going to become 16/45. X plus 6 to the power of 9/4. We already divided by 9/4. Okay, and then plus some constant. I think that's it. It looks good. Yeah. Okay. All right. Let's highlight that result. Are we still frozen? No. Are we current? As about as current as going to be. Right. So, I think that's it. Plus some constant. Okay. Stop. Okay, cool. Okay. The correct UV minus the integral of V du. Let me see if I clear that out. Right there. We got this 4/5. Where is it? I guess we need to zoom out some more. Okay. Now we got 4/5. I'm leaning towards A. 4/5. There should be an X in there. It looks like it's missing an X. If we look at B, we got our 4/5 X. 4/5 X. And then we have this X plus 6 to the power of 5/4 minus 4/5 X plus 6 to the power of 5/4 dx. All right, so B matches what we have. And then the result that we get, let's get rid of the type all this out. So we got a 4/5 X, and then we got parentheses X plus 6, the power of 5/4, okay, minus 16/45, 16/45, X plus 6, parentheses X plus 6 to the power of 9/4, okay, plus some constant, plus C, okay. Cross our fingers. Nice. All right. Okay. Let's hop back over to mail. Let's work on the next one. And again, if just, we got 2 more. If I need to go back and go through any detail, just let me know. Okay, right here. Okay. And I want to share this. Share. Just suppress you. Come on. Just suppress. Come on. Okay, that works. Right here. This current, actually, let's go like this. We want this to be live. Play and go live. Awesome. That's fine, just like that. Evaluate using integration by parts. So this one looks like we might have to do integration by parts a couple of times. Let me zoom in just a little bit. Okay. So there, here, here. Let's copy and delete. Nope. Some free space, paste. Okay. Evaluate using integration by parts, right? So we need to find our U. So oftentimes, again, when we're doing integration by parts, we're looking for a U that will help to eliminate one of the terms, right? Or one of the factors. So and we might have to do it a couple of times, right? So we're gonna let our U, I'm thinking let it be x squared. And can we integrate this dv equal to e to the 4x dx, okay? So that means our du is gonna be 2x dx. Our v is gonna be e to the 4x over 4, right? And just do a quick check by taking the derivative, okay? So it looks like we got all the parts. So then the original now becomes u times v. So we got this 1 by 4 x squared e to the 4x. Okay, I need to charge my, I'll charge that later. That's u times v minus the integral of v du. So 2 over 4 becomes a half x e to the 4x dx. Okay, so now it looks like we do integration by parts again. All right, I'm gonna just call this the next set. I'm gonna put primes on everything just to distinguish them from the original. So now our u prime, let it be x, and our dv prime is gonna be, and prime is just, I'm trying to make a distinction between the first set of integration by parts and the second. Similar thing, right? E to the 4x dx. Okay. Also, if you want, like, I think it's a free event. If you want something free in the city to do, I intend to be there. Like, if you want to, like, just find me or whatever. I want to say this Friday is a free Friday at the High Museum, right? So it's just I think it's a free event. Like the High Museum, they have like free events at least twice in every month. I think the first Fridays are free. Like it's like live music, and it's just I think it's free. I'm not sure if it's free or not, but it's just an event at the High Museum. And then the second Sunday of every month is definitely free at the High, right? So just free events to do in the city, something to just kind of take your mind off all of this stuff, Okay, so let's see. U prime, so then that means our du prime is going to be what? Dx, okay? And our v prime, the integral is going to be e to the 4x over 4, right? I think that's it. So now, the first part just persists, 1 by 4 x squared e to the 4x, okay? The 1/2 persists. So now I'm gonna put a big set of brackets. So now it should be u times v. So it's gonna be 1 by 4 x e to the 4x minus the integral of v du. So then there's a 1/4 here, e to the 4x dx, right? Okay, and close this off. So we just got to be aware that we're distributing a negative 1/2 into there, okay? So let's account for that. We get our 1/4 x squared e to the 4x. If we distribute the 1/2, the negative 1/2, we get a negative 1 by 8 x e to the 4x, okay? Plus 1 by 8, okay? Okay, and the integral of e to the 4x is itself e to the 4x over 4 plus some constant. Let's do one more update. 1 by 4 x squared e to the 4x minus 1 by 8 x e to the 4x. And then that becomes plus e to the 4x over 32 plus some constant. This is what we get. What an adventure. Truly a great adventure, right? Okay. Oh, I'm always thinking like, okay, how can we make this more simple, more clear? Because some of this stuff is kind of like, ugh, you know what I mean? Let me pause this so I can get a copy. Let's submit this. Hopefully we did everything proper. It felt right. I didn't really get stuck or anything like that. It felt like it's okay. Cause like, and it was kind of, cause like this one kind of had hints that it was similar to what we did before, but I know that one of the tricks is sometimes you got to do integration by parts more than once, right? And so you could kind of feel that in this a little bit. So then we got 1/4 x squared e to the power. My keyboard is on his last. It needs some power. I got you. Minus 1/8. Just hold on. Let me just try to get to these. E to the power of 4x. Okay. Plus 1/32. E to the power of 4x plus some constant. Okay. Oh man, oh man. Okay. Let me see how many more do we have. So we got to the trick on that one, which was the double integration by parts. We're gonna make this the last one. We got one more.
Professor,
Yes.
why did you double the integration by parts?
That's just kind of the way it worked out, right? If we back up, right? And notice that we started with an x squared. After we finished integration by parts, the x squared became x to the power of 1. So then that was the hint that, oh, well, if we do after doing integration by parts again, you can see that it's gone right here. Right. So that's just one of the tricks with these is that sometimes you do. I told him about to say do, but you do integration integration by parts twice, right? That's just what happened with this one. That's just one of the, you know, and again, the nuance is that when you're doing integration by parts, oftentimes the goal is for one of these terms to disappear, right? Because when we went from the start, it went from a power of 2 to a power of 1. So then if we did integration by parts one more time, it's gone right here. Right? Okay. But yeah, that's just one of the tricks of the trade is double integration by parts. The same way like how we were doing manipulations with the substitution, either rewriting the du or rewriting the u interval, right? Those are just tricks, the homework, or with the experience or whatever. Okay, we got log. Let's get a screenshot. Type an exact answer. All right, from there to here. Let's copy and delete right here. And let's paste. Paste, awesome. All right. Okay, let's see. That's not going to go away. That one might. What about use substitution? Let's see, because we let that be a U, that's not going to go anywhere. Nor will this one. If that's our U, we can integrate that. The integral of that. Okay. So let's see. Let's let Hmm. Okay, I don't know if I can get anything to cancel, but let's see. So I'm gonna let my u be, I'm thinking, let's go with the square root of x, right? It's not gonna cancel, but I think something else might happen. And my dv, I'm gonna let that be the natural log of 15x dx, right? So then my du is 1/2 x to the negative 1/2. And my v, thinking it's 1/15x. Let me see. No, that's not right. What's the integral log? How do we do that one? Because we know that the derivative of what? The derivative of log is the -1. Oh, do we have to treat that? Do we have to rewrite it as like an exponential or something? I feel like, I mean, that still might be the way to go. I got to think about how to, for some reason, it slipped on my mind. Let me think. But instead of, I might switch these guys around. Let me try switching these around and see if that makes it any better. For some reason I am drawing a blank on something, but I can pull it up. Okay. Let's let, what happens if we let our u be the log of 15x? Okay, and our dv be square root of x dx, okay? So then our du is going to be what, just 1/x? Because it should be 15/15x. The 15's cancel, and we're left with this, dx by x, okay? And the integral of this guy over here, our v, is what? X to the 3/2 over 3/2. This might help us. Let's see what happens. Let's try it. So then the original becomes v du. So if we flip and multiply, that's 2/3. Okay. So 2/3 x to the 3/2 times the natural log of 15x minus the integral of v du. So again, we got our 2/3. So we got x to the 3/2 over x becomes x to the 1/2. Haha, look how that worked out. That's my, sorry, my dad used to do that. Like when he was thinking about something that he would like figure it out, he'd make these funny sound effects. So he just made his presence known here. So, you know, but yeah, it seemed like it actually worked out, right? So you saw where we tried. Anyway, let's finish it out and then we'll do a recap. Okay, this looks good. So I think we can take it all the way. 2/3 x to the 3/2 log of 15x minus, now that's going to become x to the 3/2 over 3/2. Come on. So flip and multiply is 2/3. So that's going to become 4/9 x to the 3/2 plus some constant. I think that's it. Yeah. I mean, I low-key want to be like, we got lucky that they because I was like, I knew something like that would happen. At first, I was trying to integrate the log, and I'm like, I know we can do it, but that didn't seem like it was simplifying the problem. So I switched the u and the dv. So then now our du became 1/x. Our v, we were able to integrate, and then they simplified each other once we put them together. Right? So where is my thing? Did I lose it? I don't see it. It should be here. That's fine. Let's just go live. Let's get caught up. Cool, that looks good. I just want to hold that image. Let's go ahead and submit this. A little Morehouse. Took me like 10 minutes. It was fun. 2 by 3, x to the power of 3 by 2, 2, okay. Times the natural log of 15x, okay. Minus 4 by 9, x to the power of 3 by 2, okay. Plus some constant. Cross our fingers. Oh, we can breathe. I think that was the last one. Okay, Mr. Lowe, would you like to do any more, or like 1 or 2 more, maybe? Are you okay for now?
Yeah, like 1 or 2 more. Because like I tried to do question number 14.
You sent them already? 14. Just do the X-Men instructor.
Oh yeah, but I think I miscalculated.
14.
Yeah.
Okay, let's give it a go. Okay. Let's shut. 33. Okay, so that's a different one. Morehouse. Let's go here. Yeah, and then a lot of it is like taking your time, writing big and spacious. I don't know if I can do all of these, but it's okay. Yeah, let's do this. We can do it. Let's get a copy. Let's go like this. Later, let's get these questions in there. Let's copy and delete. Morehouse. Copy and delete. Okay, let's hop over here. I already could, because we don't have that much time left anyway. So it's like we need to just get these in there. Okay, let's look at this. Oh, this is what I was literally just trying to do a moment ago. Okay. Oh, integration by parts? Maybe. So if we let our U be that, okay, let's see what happens. Let's try this by integration by parts, right? Because I was literally thinking to myself, well, how do we do this integral? And I was like, I know we could do that, but for some reason, I was getting drawn a blank, right? So I'm going to see if we can do this by integration by parts. So if we let our U be the log of 13x, and we let our dv be dx, okay? So then our du is going to become, I think it's just 1 by x, because it's du over u. So that's 13 over 13x, which is just 1 x, okay? Dx. And then our v, if we integrate, is just x. Wow. Okay, that might be the case. So then, now the original is going to become a uv, so it's going to be x times the natural log of 13x minus the integral of v du, which is just dx, right? Because x over x becomes 1, right? And we want to evaluate this as x goes from 1 to 4. Same thing here, 1 to 4. So then we get x natural log of 13x. As x goes from 1 to 4 minus, what is that, just x? As x goes from 1 to 4. Okay. I think I'm going to just use a calculator for that part. Look, it's gone. This one. Okay. So let's reload and refresh. Okay, so in my y equals, I'm going to put x times the natural log of 13x, okay, minus x. And then what I'm going to do is call on that function. I want an answer when x is 4, minus that same function when X is 1. Okay, let me see. Do we have anything? Let's see. If we hop back here. Oh no. Where did we lose our window? Here, let's go to full screen. And then this needs to be like there. Okay. Do not round the 10 to 5 rest, and then round the 4 decimal places needed. So temperamental. Okay. 4 decimal places. So 10.24. Okay. Okay. So that was that one. Okay. So I think these. Go ahead.
Is that 10.24?
Yeah.
Oh, it's 10.24.
Because it says 4 decimal places.
Oh, okay.
So the four decimal places are 0. To the right of the 0 is a 2, so it stays a 0. So those trailing zeros, you don't have to put those. Integration by parts. Let's pull up this next one. We're gonna let these next two be the last two. Please don't do the wrong. I know it's gonna do that. Let me get rid of this. I get rid of that. Let's try that one more again. Perfect. That's not what I want. Okay.
Yeah, I think for question number 14, I think I miscalculated on like creating the integration by parts.
Was that the one I just did?
Yeah.
This one?
Yeah.
Right. Yeah, but yeah. So I think these are all the parts here. And I think we're still live streaming. It looks like it's working okay. So, you have a, okay. I think this is the next one. So let's get a copy. That's fine. Oops. Right here and here. Let's copy and delete. Okay, come on. We're gonna do a fresh one here. Paste. Okay. Integration by parts. Yes, right? Okay. So if we let our u be what? 7x and our dv be e to the 9x dx, then our du is going to become 7 dx, right? Okay, that's fine. And our v is going to be e to the 9x over 9, right? I think we got all the parts, okay? So now the original becomes uv, which is 7 by 9 x e to the 9x minus the integral of v du. V du is what, 7 by 9 e to the 9x dx. Okay, and then we can integrate that guy. And is this going from 0 to 1. Also, this needs to be evaluated as x goes from 0 to 1. So then we get this 7 by 9 x e to the 9x minus 7 by 9. That's going to be, the integral is going to be e to the 9x by 9. And again, we want to evaluate all of this as x goes from 0 to 1. Okay. So then we can break out our trusted dusty rusty. Where is it? No, that's not right. Let's go full screen. Um, Reload and refresh. Come on. Okay. And we are working here. Okay. So I'm going to go to my y equals. We got this 7 by 9. That should be okay. X E 9x. Okay. Minus. I just not feeling this. Let me just do this so I can be sure because I don't want. I want to keep all mistakes to minimum. It should be okay the way I had it typed before, but I just want to be meticulous. E to the 9x, okay, minus 7 by 9, okay. Actually, we can make that 7 by 81, okay. And then we got this e to the power of 9x. Close off that power. That's it. I think that's good. Okay, let's quit. So then we want to call on that function. We want to say evaluated when x is 1 minus that same function when x is 0. Okay. Okay, so we get this result. Let's see. This one. It's okay. I might need to go back and do that one by hand. Okay. Use that. We can go here. So when x is 1, we get 7 by 9 e to the power of 9 minus 7 by 81 e to the power of 9. And then when x is 0, that's gone, minus, the first term is a 0. When x is 0, that's what, a 1. So it's just minus a negative 7 by 81. Okay. So then, long story short, looks like we get 7 by 9 e to the 9 minus 7 by 81 e to the 9 plus 7 by 81. Now what we can do is type this result into our calculator and we should get the same number, right? So if we said 7 by 9, parentheses, e to the power of 9 minus 7, parentheses, 7 by 81, e to the power of 9 plus 7 by 81, okay? We should get the same number, and we indeed do, so that's promising. We want to hop back here. Let's play. Let's go live. Pause. Awesome. This is like what I need. Okay. So we can suppress that. I had a copy there, but this is just easier for me to see. Let's close this out. Open that up. So we get 7 by 9 e to the power of 9 minus 7 by 81 e to the power of 9 plus 7 by 81. Cool. Was that the last one? Let me see. Was there another one? Nope, not there. Here. Oh, we got one more. This is going to have to be the last one. Let's see what it's looking like. The rate at which, okay. Let's open it here. These are always like really interesting. Let's see. Okay, it says the rate at which electrical energy is used by the Ortiz family in 1 day in kilowatt hours per hour is given by this guy, where T is in time in hours. That is the interval from 0 to 24. How many kilowatt hours does the family use in the first hours of the day as we go from 0 to T? It's capital T. How many kilowatt hours does the family use in the first 4 hours of the day? Are they asking us to integrate? I think that's the antiderivative. Okay. Mm-hmm. As T goes from 0 to capital T. Where is the capital T? It's T hours. So it looks like we're integrating as T goes from 0 to capital T. Okay. And it looks like we can do integration by parts. So let's integrate this with integration by parts as T goes from 0 to capital T. Okay, yeah, let's do that. The rate, yeah, this is the rate, right? We want their usage. We don't want the rate of the usage, we want the actual usage. So that's why we're integrating. Okay. Okay, let me start by getting a screenshot right here. Okay, let's copy and delete. I have here and paste. Okay. So what we're gonna do here, I think what they're really asking is, they're asking for the integral as T goes from 0 to capital T of the given function, 16t e to the negative t, all right, dt. Oh no, did you just die? No, okay, dt, okay. So it looks like we can do integration by parts. If we say, let u be 16t and our dv be e to the negative t dt, okay. So then our du ends up being 16, okay. And our v is going to be e to the negative t and a negative e to the negative t, okay. That looks good, because if you take the derivative, it's going to be itself times -1, it becomes positive, okay. So now the original becomes uv, so this negative 16t e to the negative t minus the integral of v du. So double negative becomes positive, and the 16 can go in front, e to the negative t dt. And there's a dt right here. Okay. So then that guy we can integrate. Oops. So now we get this negative 16t e to the negative t plus 16, I guess it's going to become a minus, all right, because after we, the integral of e to the negative t is itself divided by -1, so that's why the 16 went from positive to negative. And then all of this, we want to evaluate it as t goes from 0 to capital T, right? So then the way we captured that, we replace t with capital T. So we're going to get negative 16t e to the negative t minus 16 e to the negative t, okay? That's not a t, okay? And then minus when we plug in 0. When we plug in 0, the first term is gone. E to the 0 is a 1, so that becomes plus 16. Okay. So I think this is the first part, and then you basically plug in when t is 4 for the second part. So let me pull this up here. Let's play. Let's go live so I can get a copy. Come on. 16. Hello. Cool. That's like what I want. Okay. All right. So let's hop here. This one. Get rid of it. All right. So then we got negative 16t e to the negative t is not a because the sign is off. Let's try e. Negative 16t e to the negative t minus 16 e to the negative t plus 16. Yes on e. I was going to consider d. E to the negative t. I think the sign is off on d. All right. So I'm going to go with e. Okay. And then for part B, basically, you replace capital T with 4 in that formula. So I think what I'm going to do is use my trusty dusty rusty. I'm just going to type it in to the function here, right? So we got this negative 16. Let's try that again. Negative 16. Instead of capital T, I'm going to put x times e to the power of, let me see. Okay. E to the power of negative x. Okay. And then minus 16e to the power of negative x. Okay. Plus 16. Okay. So then I want to basically call on that function. Come on. No. Let's try that again. Why is my enter button not working? Okay, that's fine. And we want to place x with 4. And then it says round to 3 decimal places. Let's see, he's throwing a hissy fit. There we go. 5.535, 14.535 kilowatt hours in the first floor. Okay. 535, 14.535. Come on.
Do we just plug 4 into
Yes.
these?
Yeah, we replace capital T with 4. Yeah.
Okay.
Yeah, and I did that in a function in the graphing calculator. These were some good questions. I always like enjoy your questions because they make me think, and then, okay, I think I'm spent on energy. Okay, let me go ahead and make for anybody that wants a copy can get a copy of what we were working on today. Let me see. I'm gonna send it a box. Calculus, send the box. Okay. All right. So with that, we're going to end the session here. When this bar finishes loading, you'll get a copy of what we're working on. And if there aren't any other burning questions, we'll end the session here. And from one beautiful mind to another, enjoy the rest of your day. I'll see you here for Wednesday for our last class. Take care. Peace.
Bye, Professor.